Continuing Chapter 7 on sampling distribution, Section 7.3, Day 1, Sample Means. After this lesson, you should be able to find the mean and the standard deviation now of a sampling distribution of sample means and calculate probabilities involving a sample mean when the population distribution is normal to begin with. Sample proportions arrive most often when we are interested in categorical variables. When we record quantitative variables, we are interested in other statistics, such as the median, the mean, or standard deviation of the variable. Sample means are among the most common in statistics. Consider the mean household earnings of a sample of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do you notice about the shape, center, and spread of each? Because both histograms use the same scale, you can compare the two graphs. The graph on the left is the household earnings, and the graph on the right is the mean household earnings if I were to take a simple random sample of size 100 from the population that's on the left. Notice how the graph on the left is skewed to the right. However, the sampling distribution of the sample means is relatively normal. When we choose a simple random sample from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution, very much like they were for proportions. Here are the facts. The mean and the standard deviation of the sampling distribution. Suppose that x bar is the mean of a simple random sample of size n, drawn from a large population with a mean of mu and a standard deviation of sigma. Then, the mean of our sampling distribution, noted as mu sub x bar, will equal the population mean mu. The standard deviation of the sampling distribution of x bar, denoted sigma sub x bar, is equal to the standard deviation of the population divided by the square root of n. That standard deviation formula will only work as long as the 10% condition is satisfied. Keep in mind, that means the population must be greater than or equal to 10 times the number in the sample. Note, these facts about mean and standard deviation of x bar are true no matter what the shape of the population distribution. Again, the basic concept is this. We have a population where the mean is known as mu. We continue to take simple random samples of size n, find the x bars, and then plot them. If we do this for every possible combination of simple random sample of size n from that population and graphed it, it would be the distribution on the right, where the mean of x bar would equal the mean of the population, and the standard deviation of this sampling distribution would equal sigma divided by the square root of n. We have described the mean and the standard deviation of a sampling distribution of sample means x bar, but not its shape. That's because the shape of a distribution x bar depends on the shape of the original population distribution. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal to begin with, then so is the sampling distribution of x bar. This will be true no matter what the sample size is. Sampling distribution of sample means from a normal population. Suppose that a population is normally distributed with a mean of mu and a standard deviation of sigma. Then the sampling distribution of x bar has a normal distribution with a mean of mu and a standard deviation sigma divided by the square root of n, provided that the 10% condition is met. So let's take a look at an example. The heights of young women follow a normal distribution with a mean of 64.5 and a standard deviation of 2.5. This is my population distribution. I want to find the probability that a randomly selected young woman is taller than 66.5. So I'm going to let x equal the height of a randomly selected young woman from this normal distribution with a mean of 64.5 and a standard deviation of 2.5. I'm going to find the standardized z-score for 66.5 inches, which ends up being 0.80. And I'm trying to find the probability then that z would be greater than 0.80. Since the normal table works on the lower half of the distribution, I will take 1 minus the probability that z is less than 0.80, which would be 1 minus 0.7881, which gives me 0.2119. The probability of choosing one young woman at random whose height exceeds 66.5 inches is about 0.21, or 21%. Next, what I want to do is find the probability that the mean height of a simple random sample of 10 young women would exceed 66.5 inches. So in this time, instead of just one woman, I'm looking at finding a simple random sample of 10 and averaging those heights together and finding the probability that that average height would be greater than 66.5 inches. This no longer deals with the population distribution. It's going to be dealing with the sample distribution of a sample mean. So for a simple random sample of 10 young women, the sampling distribution of their sample mean heights will have a mean and standard deviation that's given below. Mu sub x would equal 64.5, and to find sigma sub x, I would take the standard deviation from the population, which is 2.5, and divide it by the square root of the number in the sample, which is 10. So you can see here my standard deviation becomes much smaller at 0.79. Since the population distribution is normal, the sampling distribution will follow a normal distribution with a mean of 64.5 and a standard deviation of 0.79. I will then again standardize my z-score for 66.5 inches tall. But since it's coming from a sampling distribution of sample means, the standard deviation is much smaller. So my z-score in this case of an average of 10 becomes 2.53. Finding the probability that the z-score would be greater than 2.53 ends up being 0.0057. So you can see that averaging 10 together, it's much more difficult to find an average of 10 young women heights who would exceed 66.5 inches on average than just a single individual young woman who is taller than 66.5. It is very unlikely, less than 1% chance, that we would choose a simple random sample of 10 young women whose average heights exceed 66.5 inches. If I take a look at the graph of the population distribution and the sampling distribution of x bar at the same time, you can see that the sampling distribution of x bar has less variability. So you can see the area under the curve under my sampling distribution would be a much smaller area than the area under the curve for a population distribution, just finding one woman whose height is greater than 66.5. In tomorrow's lesson, we'll take a look at what we do when the original distribution is a skewed distribution or another type of distribution that's not normal.